So my name is Anup Nair. I am the CTO for Mphasis AI. And this is Bharat.
I'm Bharat, Senior Partner in Mphasis.ai.
So we are going to talk about legacy modernization and Mphasis framework, Agentic AI framework for legacy modernization. That's what we're going to talk about. We have some exciting demos as well as part of this thing. So I'm hoping you'll like it. And if you have any questions, please feel free to get us offline. I don't think they allow us questions here, but yeah, why not, right? So to start off with, let me give a little background here, right? Let's discuss the problem statement first. In the last 25 years, every CIO I have met, this is the problem. I can't innovate fast enough because it's too risky to touch any legacy platform. Are you guys on the same page when it comes to this? In fact, one of the CIOs actually told me that I have 49 core systems that are built on COBOL mainframes, and if I touch one of them, I have to touch all the remaining 48 as well. So this is the problem we decided to solve. Mphasis.ai has built many different agentic AI solutions to solve these problems. So Mphasis has an experience building and modernizing legacy application for many years. So we're going to talk about this, but more importantly, I think I want to double click on the problem a little bit more to really understand the genesis of our solution, really describe the solution itself. So, the problem with legacy system is that enterprises are anchored on these systems for years, and these systems have code, business logic embedded inside code for years, right? And every time you want to do something, you need engineers, right? You need business logic, this is in COBOL, this is in Java, or it could be natural database, or it could be assembler for that matter, right? It could be all of those kind of systems, but you need specialist engineers to handle this. These engineers are not easily available. They're not in the market. They're out of the workforce at this point in time. Therefore, you start reinventing the wheel, keep reinventing the wheel on an ongoing basis, and you start creating a lot of technical debt. Now, any change is too costly because you're doing it at 10 different places, and you're connecting, creating layers and layers and layers to solve the problem because you don't know what's actually going on. So now you think about this and you decide to put AI on top of it, agentic AI, right? You're driving innovation, you need to put agents, right? Whether it is agents around claims or agents around underwriting or whichever agent. You want to put agents on top of this. Think how it is going to be. Because all of these legacy systems are so deeply monolithic, it is extremely hard for any agent to give you any productivity. So all your agentic AI objectives and goals goes for a toss. Just because you have this is the reason why modernization, this is the reason why any innovation is so slow, because you have to touch everything out there. So we at Mphasis, we thought about this, and we said, okay, it is really not just about technical modernization. It's not just modernizing COBOL to Java or natural to Java or C to something new. That is not the point. It's about taking the intelligence out of the legacy systems and converting that into data. That should be the goal, as opposed to just modernizing code from A to B. That is exactly the approach we have taken. So let me talk a little bit more on how we are about to solve this thing. But for that, how do you typically modernize? Are you aligned to this, everyone? First you relearn from your legacy systems, then you reimagine, then you re-architect, and then you recode. And then you start running it. This is how you do. You take COBOL, and you convert it into Java, and you start managing it again. In about 3 years' time, that becomes legacy again. This is how you typically do it, right? So what we have done is slightly different approach here. We've built agentic AI agents that are autonomous and semi-autonomous with human in the loop, because anybody who says that everything is 100% autonomous is joking. It's not, okay? So we took documents and code, we built an agent called NeoZeta. And this agent actually reads everything, converts everything into human understandable knowledge. How do you do that? We use domain knowledge, Mphasis domain knowledge, to really make that happen, because we have encoded them. We create a knowledge graph. And then we thought, okay, now we have a knowledge graph. How do you take this and create a new system? What do? You generate user stories out of it. So we created another agent. We call it NeoSaba. This agent takes everything that you've learned, converts into user stories, and focuses on governance, focuses on compliance, focuses on processes, business processes. SABA stands for semi-autonomous business analyst. We take that and we allow a business analyst to work on it. We then convert whatever we create out of this, we put it back into the knowledge graph. Now what's next step? You reimagine or re-architect. We've created another agent. We called it NeoRena. This is an agent that will take everything you've learned and helps you define the target state architecture. This target state architecture is customizable for you, for the client, and everything you create out of this aligns to enterprise standards. The reason why it's customizable is because you need to make sure that it aligns to enterprise standards. Okay, so once you create that, then all the architecture is done. You take that and you rewrite. We've created an agent called NeoCrux, which takes everything, allows you to prompt. It uses whatever coding agent is available in your enterprise and starts writing code out of it. Continuation to ops as well, right? Why not? You've built everything, you put it into production, you've tested it through Crux and all, now you're putting it into production, you need to run operations as well. But all through this, we've built a connective tissue. We've extracted the intelligence out of the whole thing and created an enterprise knowledge graph. That enterprise knowledge graph is not just a database. Knowledge graph's a database, but this is not just a database. It has meaning. It has enterprise meaning because it is connected to your domain. We called it Ontosphere. And then we used a layer on top of it to orchestrate the whole thing so that we can get it as autonomous as possible. So this is Mphasis' approach to modernization. Now, you will see some of them are autonomous, some of them are semi-autonomous. As AI progresses, as context abilities grow, this will become more and more autonomous. And essentially, you create a live intelligence of the enterprise. So what you are going to see today as a demo, you're going to see NeoZeta extracting intelligence out of code. You're going to see NeoSaba allowing the business user to create user stories. You're going to see NeoRena, you're going to see NeoCrux, and you're not going to see AI Ops because we didn't have enough time, but you're going to see a glimpse of Ontosphere as well. So you're going to see 5 things: Zeta, Saba, Rena, Crux, and Ontosphere. Okay? So I'm going to switch to a demo and let Bharat walk you through a whole suite of things. Bharat.
So let me start with first talking about Ontosphere, because this is where the heart of the information lies, right? Every knowledge in the system, whether it is code or document, is going to be brought into as data on the Ontosphere. Now, we're using a couple of domain ontologies we are using a couple of domain ontologies which have been built up, which is on the financial industry, insurance, and other industries. We have also kind of really put in a couple of engineering ontologies, which is through our agents. Okay, this is the basis on which a lot of modeling will be done into the system. Let me go to the first agent. So this is NeoZeta. As you see, NeoZeta, I've selected a program, I've selected a capability, and we took a very complex capability in terms of the post-trade processing, because this is where you have a process which stops at 4 o'clock. You have maybe millions of trades which have to be processed, and files have to be sent to the federal authorities. So we took this problem. We said that the only way that we will be able to solve this is pick up a lot of intelligence from each of these processes which have been coded in legacy COBOL. This is an example of COBOL that we're showing you. And then reverse engineer it, and post that help to kind of really modernize it using our agents onto a Flink-based architecture. And I'll show you a glimpse of how did we execute it on a CPU as well as on a GPU, how the performance varies. So continuing with our demo, I have selected the capability. I have capability to upload my files, which may be documents, which may be different assets. I've uploaded COBOL copybooks, and I've also uploaded, as you see, a domain model out here. So these are the programs that you see, and this is the domain model that I've uploaded. Using the relearn agent, I'm actually relearning each and every program or an entire capability. So as you see, I've actually selected a program which is Quantiles along with copybooks, and I'm doing a reverse engineering of it, right? So there is so what it does is it has capabilities to generate the data dictionary. Now, we haven't fed any information, but you see that there's a good amount of information that it has brought out from the system, and it's starting to map it with the actual functional attributes. And I'm also showing you the document that it produces. The document has a certain format. It produces summary. Then for each and every business rule, it will start providing me a lot of data elements, as you would see, right? It'll give me the logic, it'll give me the input, it'll give me the data affected, it'll give me a lot of other processing elements that I would need as part of relearning a certain code. Now, the most important piece is, how do you verify that the system has done it very accurately? So we've introduced what is said LLM as a judge, and it gives me a confidence score for every rule that has been reverse engineered. As you see, it tells me that one of the rule has got an average coverage, which is 85%. For us, 85% is average. Anything above 95% is something which we'll kind of count it as a better one. But it tells me so that there is a human in the loop interface over here. I can go and make corrections over here. The first 100,000 lines of code typically need such corrections, but then for the next million lines of code, it's an automated way where you get 95% accuracy from the relearn agent. So we've produced data dictionary, we've produced business rules, and you've seen the business rules verification as well. The third part is to convert everything onto the ontosphere, which is the knowledge graph. And which is what, let me demonstrate that to you. It's just showing you some of the attributes from LLM as a judge. So I'll go to the knowledge graph right now. Actually, before I go to the knowledge graph, it has produced information also for the entire capability. So you have a model to take program by program or for the entire capability. Typically, if you have a big job which is running and multiple programs in it, multiple processes, you would like to see such a view in terms of bringing the entire intelligence out. And finally, the third step in converting it to a knowledge graph. So if you look at it, I've picked up one of the programs which are reverse engineered, and it is showing me which are the domain models that has been associated with it. I can double click on functions, on the attributes, on the information, and this is something that SME can use it for verification purposes, right? So essentially, everything that you saw earlier was the first agent. This is where the information comes to the second agent. All information is put up as part of the business process. This was exactly the graph that you saw earlier. It's coming now in a business as a workflow item. And I can leverage this, look at it, and start reimagining my application, which is in the top section out that you would see. I can even pick up business rule-wise, combine multiple business rules and create a new rule. So we've given those capabilities out there. On the top, what you're seeing is essentially nothing but an overall agile remodeling of the application. So I'm completely reimagining it. It's not a lift and shift model that we have. I'm helping the BSA define the epics, features, user stories. And for every user story, there is an assessment done on the quality of the user story through the invest score. As well as you have a prompt mechanism by which you can generate acceptance criteria, generate a lot more information. So you see the Gherkin output over here. We actually create BDD at this point in time. So quality essentially starts for us at this point in time. This is the prompt where I can generate information in the form of if it doesn't meet my invest criteria, I can further break it down into many different rules. So I'm going to the third agent in the interest of time. From a third agent perspective, now my important part is to re-architect or redesign it. So I've created, so over here what is needed is three things, right? Actually two things. One is a playbook about the steps which we have to do in terms of reverse engineering, and second is the standards that I will use. We've given both as an input, and I'll just show you how do we do this, but it started to give me all information, whether it's a logical model, or it's a physical model, or it's a sequence diagram, or it's an observability pattern that has to be leveraged. Everything which has been fed as a standard is being brought up by the agent, which is Raina, the third agent that Anup spoke about, right? The job of this particular agent is to build the entire context and make a prompt ready for my next agent from a development perspective. So if you look at it, I'm generating right now, I've fed the information that I need to generate it using a Java Flink model, okay? I've just shown the step how fast you can actually do it in the interest of time. So I'm trying to create a new design, and I've given to it, I'm giving to it the playbook as well as the standards which have to be used. I'm using data engineering architecture. I'm giving the playbook for the standards, which is the Flink one, and I'm generating the entire context. So all information pretty much gets generated from that perspective. Now I'm going to my fourth agent, which is the code generation agent. Now it's a, this gets the entire information and generates code from a Java Flink architecture perspective. What you essentially see is an example of how this ran on the GPU as well as it ran on the CPU. So there's a big distinct difference in terms of the timing that you would see if you run, we've modeled it for multiple sets of trades. So example, if I go from 20,000 trade to 100,000 trades, what will be the cost from a CPU perspective versus the GPU perspective? And we help them to make a call from a job by job perspective. Enough. So that was one I had to show. Let's go back to the deck.
So guys, this is what we have seen so far from a results perspective. We've achieved this. A typical modernization program with about 50 million lines of code takes around 7 years. Okay? We've achieved this kind of progress. That infinity at the end, guess what it is? It is the fact that your entire intelligence moves into data and lives with you forever. You never have a legacy, right? That's the thing, and this is we kind of put together, how are we different from anybody else? There are a lot of people you'll get who move A to B, but very few who will extract intelligence and give you a state where you'll never have a legacy anymore. So that's what we wanted to cover today.
And
We're time up.
our agents have actually run on DAppStab. So they scale up pretty high on that. So we've constantly measuring it, monitoring it from that perspective.
Thank you, guys.
Thank you, guys.
That's all we had. The time is up.
Thank you.
Thank you so much.